That's fine. Thank you very much.
Okay, well, let us start. So for the first lecture of the second day, we are happy to have Laura Donnay, and she will continue to talk about celestial amplitudes.
Thank you very much. Good morning, everybody. Thanks for coming. So yeah, we will keep exploring this topic of the infrastructure of gravity in flat spacetimes. Let me start by summarizing the main point that we saw yesterday in the first lecture. So yesterday I tried to present the rich fact that the symmetries of asymptotically flat spacetime are way bigger than the ones of Minkowski. Asymptotically flat spacetimes, and we saw a precise ansatz for the metric which is asymptotically flat as one approaches the boundary, the null boundary, future null infinity. So the symmetry of exactly flat spacetime are given by the Poincaré group, which consists of 4 translation and 6 Lorentz transformations. Now the symmetry group of asymptotic flat spacetime is an infinite dimensional enhancement of Poincaré, given by an infinite amount of what people have been calling super translations, which are spanned by these arbitrary function of the angles t, which comes in these u components of the infinitesimal vector field. And similarly, there is a sense in which we can enhance the Lorentz part of the Poincaré group to an infinite amount of super rotations. Spanned by conformal killing vectors. So we have 2 copies of them in these complex coordinates, y, which depends only on z, and y bar, which depends only on z bar. So these are conformal, local conformal killing vector on the sphere. Okay. So this is what is known as the extended BMS group. Extended because in the first place, Bondi, Messner, and Sachs only found these super translations, but now people thought it was a good idea to extend the Lorentz part to also an infinite amount of symmetries, because in conformal field theory, we are very used to having this Virasoro type of symmetries. So this is what we saw yesterday. And today, I want to tell you basically on the importance of these symmetries for the scattering problem in flat spacetime by showing you that these symmetries provide an infinite amount of conservation loss for the S matrix. And so this is the relation we will start looking at, the BMS and the S matrix. So this is a result due to Strominger. Is now already a bit less than 10 years ago. So the result can be stated as follows: BMS symmetries imply an infinite amount of conservation laws which constrain strongly scattering amplitudes of massless particles in flat spacetime. So the original references for these papers And to show that, of course, I will not have time to go into the details of all the steps required for establishing such a correspondence, which is a neat mathematical statement. But I want to tell you what are the two main ingredients you need in order to achieve this. So the first ingredient is given by BMS charges. So far, I've been telling you about symmetries, but as you know from Noether's theorem, when you have a symmetry, there is a conserved quantity associated to it. And the BMS charges are nothing but the Noether charges associated to these the asymptotic symmetries. To the BMS, of course, asymptotic symmetries. So you might, actually, this topic of building charges associated to asymptotic symmetries is a whole topic on its own in GR. So it could be a lecture just about that. There are many techniques involved, which trace back to the work of Wald and Zupas and other people in the 90s. It's known as the covariant phase space formalism. If you're interested in knowing how building these charges, I would refer you to this PhD thesis, which I think contains the most accurate and state-of-the-art prescription for BMS charges. But let me just give you one result, what this charge is for a super translation. So I will denote by QT the charge associated to super translation symmetry. And this is just taking this simple form. So where it's basically a pairing between this function of super translations and the mass. You remember this M was the Bondi mass aspect that enters into this 1 over R expansion around flat space. And this integral is over the sphere located at the past of the future of null infinity. So I will have to define this because I don't think I did it last time. So you remember we had this null boundary, future null infinity, scribe plus, which was parameterized by retarded time u and coordinates. Now, if I take u goes to minus infinity, I arrive here at the past of future null infinity. And similarly, we had, I didn't present the things in advanced coordinates, but as Francesco was asking, there is all these stories also valid for incoming particles. And in this case, everything is labeled in terms of this advanced time, v, which is t plus r. And taking v goes to plus infinity, you land on this location, which people denote by prime minus plus. So it's the future of the past boundary. Here. So v goes to plus infinity. Okay, so yesterday I've been writing everything in terms of just one component of this boundary in terms of scribe plus. And so strictly speaking, I have defined for you one copy of the BMS group living on the future. So I will denote with a plus, yes, the charge living meaning on future null infinity.
Hi, one question. What is the qualitative difference between the past of the future null infinity or future of the past null infinity and the spatial infinity I0?
Yes. So we'll come to that, but so I0 is here. And on this diagram, it looks like they are the same thing. But actually, it's just an artifact of this Penrose diagram. Actually, these locations are infinitely far away. So, and actually, more precisely, spatial infinity is not included into the conformal compactified spacetime. So this is actually a very important point, and I will come back to it right now about how do you basically, what happens when you cross this spatial infinity. But yeah, spatial infinity is not neither square plus minus, neither square minus.
Not at the limit point of this.
Yeah, it's strictly speaking, I could not even draw it here in this diagram.
Thanks a lot.
Thank you. So I have told you about BMS here on the future, but there is another copy of BMS symmetries on the past. And this charge will denote the BMS charge living on the future. But there is also, there exists also a charge living now on scribe minus plus. So that's the first ingredient, is actually to be able to construct these charges. And now you probably see where I'm getting at. What I'm getting at is that in order to define the scattering problem in flat spacetime, we need to know how the quantities that are defined at the past are related to the one living in the future. So in order to make this statement true, and actually to uncover that BMS symmetries provide you a symmetry of the S matrix, a fundamental ingredient, and this is, I think, the lack of observation of this statement was because nobody really realized what we needed to do to match these two disconnected pieces. And Strominger proposed that there is a precise way to map the quantity of the spacetime from the past to the future through so-called antipodal matching at I0, but let's just call it antipodal matching. So this antipodal matching will give us a junction condition for a gravitational scattering problem. Again, I'm focusing on massless scattering, which is needed to relate the incoming states to the outgoing states. So without such a matching, you cannot talk about scattering, basically. So what is this antipodal condition? Well, antipodal just in the sense that we will relate quantities on the celestial sphere as scribe minus plus with the one at the antipodal point of the sphere at scribe plus minus. So to do that, you can consider, you remember I used these ZZ bar coordinates. So a convenient choice for these coordinates is to say that a point Z and Z bar, the coordinate ZZ bar, will represent a point theta phi on scribe plus, or the antipodal point pi minus theta, pi plus pi on scri minus. So this is just a way to choose my coordinates here in such a way that when I will give you a ZZ bar, it will either represent a point on scri plus or the antipodal related point on the past. This is just a way, it's just if you want a choice for these coordinates that will make this antipodal matching way easier to write down, because now basically this coordinate system implements naturally this antipodal relationship. So what it means is that, so the condition that we will impose is that the Bondi mass aspect, so it also depends on you, evaluated at scri plus minus, will be equated to, well, okay, u goes to minus infinity, so I will not write it down because it's not a function of u anymore, strictly speaking, on this location, will be equated to the sphere, to the corner at scri minus plus. So that's the antipodal matching condition we will impose. And it's really crucial because not only without that, you cannot make this statement about the asymmetric, you cannot make any sense out of that. And second, we will see that this condition is actually the one needed and very natural to a certain amount of extent. For instance, you can see that this is PT and Lorentz invariant, and there have been a long literature in general relativity about this sort of matching condition. So it's a very difficult problem to see in general how the field will behave when you take u goes to minus infinity. It's a delicate problem in GR and how they evolve from the past to the future. So yes.
So in general, M is different before the limit. So you have mu ZZ bar on scri plus and some M tilde V ZZ bar, and then in the limit you do this term, or the function as a function of U and V is supposed to be somehow related. So why you use the same symbol, so to say?
Yes, yeah, very good. So indeed, in principle, the M here is this 1 over R term is in the GVV components of an expansion of BMS type at scri minus. So in principle, these are two unrelated quantities. But now, indeed, I'm making the claim that if you want, yes, this in principle would be a different function. But now I'm identifying this function at these corners.
So is there a physical intuition between why you want this condition? Like I understand maybe the math gets better, but
yes, I mean you can see that if you are a non-interactive particle and you enter the spacetime from the past infinity, you will cross the sphere at scri plus at the antipodal relation. That's somehow natural in this sense. But it's a really non-trivial statement about the structure of the space-time, which is, so I want to emphasize that this thing is, has not been fully proven, but it's proven in a posteriori when we will see that it's equivalent to the Weinbergs theorems. So it gives a proof a posteriori that this matching should hold.
Sorry, maybe you also mentioned that this is it seems that it is an artifact of the Penrose diagram that these two places are the same, no? But they are not the same.
No, they are not. Yeah,
okay, so for other quantities, this matching is not true.
Other quantities, what you have in mind, like other
the other terms in the expansion, for example.
Yes, yes. So I will also impose this matching on the other function. Here I'm doing everything for super translation, so this will be enough. But it also matches. You remember this angular momentum aspect we saw yesterday? This will also be matched, and also the shear. This gravitational shear will also be required to obey a similar antipodal condition.
Okay, but so if you match all the quantities there, it is not like if you are imposing that these two places are the same. You can analytically continue all the function in I0. So it seems like you are identifying these two.
So these quantities are not strictly speaking defined at I0. There was an expansion over around the null hypersurface. And if you want to give me a data on, like there are people do on some kind of time like Cauchy slice, you will have to do a total, and you want to describe an asymptotic expansion around a spatial infinity, you will have to resort to a totally different gauge and stuff. So these are a lot of work by Friedrich and other people where you have to resolve a space like infinity by either you can put a system of coordinate and foliate it by hyperbola, or you can use another gauge where you foliate it by, well, you describe I0 as a cylinder. There are many ways to do that, but there are really different expansion around I0. And since I will be interested in massless scattering anyway, no massless particle goes there. So it's we will not need to do that for the purpose of this lecture. But it's an interesting story, and people have been looking at BMS symmetries around I0. Okay. So now that we have this matching on the phase space, so I will not enter into much details, but I'm actually restricting myself to a certain class of spacetimes, which are the so-called Christodoulou-Kleiner-Mein kind of spacetimes, which obey certain conditions. I don't want to go into too much technicalities about that. But if you're interested about the assumptions behind this, just you can ask me at the break or during the discussion. So this antipodal condition will break the combined BMS plus. So in principle, we have two copies of the symmetry, one living at the future, one at the past, BMS plus and BMS minus action, which act in principle independently on the future and the past. It will break it down to a diagonal subgroup that preserves this antipodal condition. So basically what he will amount to do is it will amount now to identify the super translation parameter at the past of the future with the one of the future of the past. So again, in principle, as Marco was making a point, this T function is in principle a very different function, but now if I want to preserve this matching, it will induce this choice, which basically fixes one frame in terms of one other. And so we have this symmetry matching now, as we are going through around I0. And now we can put the two ingredients together to show immediately that what this matching will amount to do is it will amount to equate the BMS charge at the future and at the past, which is the statement that the energy is conserved. This we know, but now the super translation enhancement is telling us that the energy is conserved at every angle. And the quantum version of this equality is a wired identity. So the wired identity associated to super translation symmetry is the statement. So if it's a symmetry, it should commute with the S matrix. So this will be the form of the wired identity that is implied by a super translation symmetry. And I will tell you briefly how you can see that this wired identity is actually nothing but a very well-known theorem in quantum field theory, which is Weinbergs soft graviton, where soft graviton is a graviton whose energy is taken to 0. So I will present the main things we need in order to show this sort of statement by getting at a more defined, more affinated definition of massless scattering in flat space, where I will introduce the things that we are more used to now in quantum field theory with free fields, creation, annihilation operators, and most of the work to show these identities to actually translate these two languages, the language of general relativity and asymptotic symmetry and charges with the one of the quantum field theory that we are more used to. Is there any question on this conservation? So, yes.
The reason that we don't need this condition for simple flat space scattering is this that M is 0, or is there something else? Because I think there's a discussion in Weinberg's book about matching the generators of Lorentz group for the inner state and outer states. Is this related to this?
So the first part of your question, no, don't keep the microphone because I'm not sure I understood the question. You ask about what is 0 if this thing doesn't hold, what?
The quantity M, the bonding mass.
Yes, so what's the question is whether this holds.
I mean that this condition is trivial for simple flat space scattering. I mean, why we don't bother to talk about this?
Oh, yeah, no, because we are interested into, you know, this asymptotic flat space, phase space with and how this Bondi mass. I mean, Weinberg doesn't care, I guess, in the Bondi mass aspect and the angular momentum. This is just a different point of view. It's just really two communities talking different languages and working in a different setup that never came into the realization that they were actually describing the same physics in different ways. Yeah. So then let's go to massless scattering in flat space. If there is another question, just interrupt me. So I will sometimes, okay, I will write down very fast. Now I will be using, I mean, usually we are using not Bondi coordinates, but Cartesian coordinates. And I just want to write for you how these two things are related to each other. Just a simple change of coordinates, but again, most of the work has to do with translating things into one another. So this is just a change of coordinates from Cartesian to this Bondi coordinate I used yesterday. And this maps to the line element we had yesterday. With gamma z bar, the round sphere metric. So a massless particle of energy omega will cross the celestial sphere ES at a point. So now I will use a different notation, but it's not different notation. I will use different letters to distinguish the coordinates Z and Z bar, and the coordinates that label the momenta of the particle. But this W bar, not to be confused, the omega with the W. So I hope this will not lead to confusion. But you have you can parameterize the four null momenta of the particle, P mu. So the on-shell massless particle, like so, where omega times q mu, where q mu is a null vector, which can be parameterized like so, in terms of these angle W and W bar. So this parametrization is not unique, of course, but this is very convenient when we want to match things with boundary, because you can see when you see how you go from Cartesian to boundary coordinates, this parametrization looks not so crazy. And the particles, so I will be talking about spin 1 and also spin 2 particles, mostly about gravitons, but they have a polarization vector epsilon mu with a plus denoting positive helicity, which in terms of this null vector parametrization for Q can be taken to take this form. And similarly, for negative helicity, epsilon minus can write it like so. So you can check that these guys satisfy these relations. So they are suitable polarization vectors, normalized like this. And okay, very good. So this is just mostly introducing notation. So what is important is that we have massless particles. They have an on-shell momenta, and I can write, instead of writing P mu, I can write everything in terms of three numbers: omega, the energy, and a point W and W bar at which the particle will cross the celestial sphere. So this is the most very natural thing to do. And now we will want to talk about, let's take mass scattering of a gravitational field. So at late times, the graviton will become free and can be approximated by the mode expansion that I guess you're all familiar with. So I'm considering an outgoing graviton, which is at very late time is free. And this is the usual textbook formula that you can find. But I have to write down just to introduce my conventions and notations where you have the usual creation and annihilation operators, exponential of I to the p dot x, where x are the Cartesian coordinates. And you have a sum over the two helicities, plus and minus, labeled by this alpha. A out dagger, e to the minus I p dot x. And now we have a polarization tensor. It can be plus or minus helicity, which is, we're choosing a gauge so that it can be written as epsilon mu times epsilon nu. And A out and A out dagger satisfy the usual commutation relations. Write it fast. E prime dagger is delta alpha AB times 2 omega. Omega is P0, 2 pi cube delta 3 of P minus P prime. Okay, so I'm guessing you have seen this expression before, and now the main thing we have to do is we have to express this expression. Well, express is tautological. You have to write down this expression in boundary coordinates, u or zz bar. And take a large radius expansion if we want to match it with the BMS asymptotic expansion that I wrote yesterday. And then what you can show is that it will take the following form. So remember that what I introduced yesterday, this shear function, so this encodes the two polarization modes of the graviton, was the piece in the ZZ bar components of the metric. So to extract it, I need to take the perturbation h, divide by r, and take the limit as r goes to infinity of this quantity. So this is just a definition. Now it's an operator. You see, I have operator representation for this object in terms of creation and annihilation of gravitons fields, gravitons. And so this is a definition if you want, but it will match, it will be identified with the shear in the BMS expansion. And now you need to do this business. Write down H in boundary and take the large R limit. And there is a little computation to do that I will not review here. I'm just writing the result. Minus A minus out. This depends on omega. That's bar. You have a dagger and you have exponential E omega U. So to obtain this, there is, you see, you need to write this in boundary coordinates and take the large R. So there will be a rapidly oscillating phase in this exponential. You need to take stationary phase space approximation that will localize this exponential. And it's done in detail in the exercise in the book of Andy Strominger that I've written the reference yesterday. This Strominger lecture notes. You can see the detail in these exercises. But the important thing I want to emphasize on is that doing this large R expansion will localize the point the direction in momenta on the celestial sphere. So you see, before I made a distinction between the ZZ bar coordinates of the point in space-time and the point WW bar at which the particle is pointing towards the celestial sphere. Now I'm doing this large R expansion. These two angles will be identified. So I have only now something that will depend. So omega and omega bar have been identified to Z and Z bar. So this is this little computation that does this. It's just saying that we are identifying the point on the celestial sphere at which the particle crosses, scribe plus and scribe. Well, here I'm talking about outgoing state, so scribe plus. So I can pause here. If there is some question on the notations or on what we are doing.
Sorry, Laura, a very elementary confusion. So typically when we have particle states, we take, say, a graviton with a definite momentum. So here we are integrating over this energy. So what is the relation with the usual particle states? Can you repeat again?
So here I'm integrating over, yes, if you want, this is the expressing the state in a direct or position space, which is related to the momentum space by a Fourier transform. So it's because you see so basically this is basically a Fourier transform which inverts the energy with the time, because I need to map precisely, I need to express this in this basis to map it with the Bondi story.
But the state is going to be, say, eigenstate of boost, or what? The associated states will be an eigenstate of boost, or?
So the associated state. So usually, let's see. Yes. So usually they would be in. If I were in the position in the usual momentum space, there will be energy eigenstates. Now, if you want, they are the Fourier transform of that. So they will the transformation will be a bit, the thing that they will diagonalize will be a little bit different. So then eventually I will go to another basis. I will not stay very long in this U basis, if you want. I will go into the celestial basis where things will transform nicely under boost and Lorentz transformations. So yeah, it might be a bit not familiar to write the graviton mode like so, but precisely most of the things to establish the connection between these two topics is precisely to sometimes go to some bases which are not so conventional from one point or the other. And at the end, I will go to a totally different basis.
Thank you.
Hope it clarifies the things. So this is for graviton, and you have an analogous expression for a spin one particle. Let me, yes, I mean it's very similar, but in case you prefer that, so. Well, okay, I think I'm running out of time, so I will not write that, but basically you have a similar expression for gauge field, a mu, so the Z components of that. And I'm selecting the leading piece in the large R expansion, which now normal fall off for a gauge field is to start with R to the power 0. And idem, except that here instead of you will have epsilon Z instead of ZZ. Yes, maybe I should say what this this hat here is 1 over r squared times this epsilon I have defined here. And here the okay. So this is, so what is this expression means? Again, to reiterate. So let me call this expression 1. So here you will really have the same expression. You can find it into Andy's book, where epsilon hat is epsilon z divided by r. The powers are a bit different than from gravity, but okay, so let me write some words. So these will define for us boundary operator living on scry. So these two operators, 1 and 2, what they do is they annihilate a positive helicity okay. Graviton or photon. Graviton for expression 1, photon for expression 2. And they create a negative, so outgoing. Graviton or photon at the retarded time u and at the point z bar on the celestial sphere. Okay, so here you have CZZ, so we describe one helicity, but you have a similar expression for CZ bar, Z bar, with some details change about the polarization and so on and so forth. So does this make sense? I hope. So this we have a sort of a boundary operator that lives in this null hypersurface. And now what I will tell you is that the zero mode of the field strength associated to these boundary operators, once inserted into the S matrix, actually leads to this universal formula known as Weinbergs theorem. I will not have time to review in details some theorems. I will just sketch very schematic way what these are. Good. So this traces back to the 60s also. So it's funny to notice that it was at the same time that Bondi, Messner, and Zach did their work. Weinberg on this side was studying the infrared structure of scattering elements, and other people like Lowe, Burnett, Gell-Mann, and others. So a soft theorem is a statement about S matrix, which involves a soft particle. So let me just sketch what these are, and you can go into the Weinbergs literature if you want to know more on that. So it's basically saying that you have a scattering process involving a certain amount of particles, which all carry a momenta. And you add to this process a soft graviton or soft photon, but let me focus on gravity, which will, whose momenta will be written like this. I'm calling just k mu. Now, in the limit where the energy of this soft guy is taking to 0, these things will, this amplitude will factorize and will be given by the same amplitude, but now without the soft one, times a number. And this number is called a soft factor. So, roughly speaking, you have an amplitude with n particles. So these particles, which are not soft, are sometimes called hard. This amplitude will factorize as omega goes to 0. And like so, where S0 is the soft factor. Let me write down what this factor is for gravity as 0. So it's just a number. Which only involves the momenta of the hard particle and a pole, Weinbergs pole. So importantly, this pole goes like omega to the -1. And this etas here is just plus or minus, just +1 if the particle is outgoing and -1 incoming. So this theorem is called universal because the form of this amplitude factorization doesn't depend on the nature of the other hard particle. Remarkably, there is a sort of universality into this formula. It holds for gravity, but also for scattering of photons and also of gluons. There is a soft photon theorem, a soft gluon theorem. The form of the factors are, of course, different, but very similar. And now I can, in the last 5 minutes, I can basically tell you the main conclusion that I wanted to get at is that the VMS symmetries, this word identity that I've written before, once we do this dictionary between Bondi and Weinberg, they are exactly the same statement. So I will just, this will serve as a sort of a review, and it will help me to also extend what I've been presenting to other cases. Just a summary table. So we have this word identity. If you remember, this was the statement that the S matrix commutes with the super translation charge. So what am I trying to say? So we have a graviton. We take this Z bar component. We read of the shear out of that. And then yesterday we saw that the asymptotic symmetry of flat space includes super translations. Psi t by du. There are super rotations, y, yz, dz plus yz bar, dz bar. And the thing I'm claiming, and that Strominger and others proved in a rigorous way, is that this war identity associated to symmetries gives us Weinbergs theorem. So the leading is the one I have written here, which contains a pole in the energy. I will come back to this subleading story in a moment. But before that, let me just say that if you have a photon, you make a similar expansion. Here, a scry. You have now the gauge version analog of these symmetries, which what people call a large gauge symmetry, which basically changes the field like so, where the epsilon is an arbitrary function of the angle. And the war identity associated to that is now, not surprisingly, the leading soft photon theorem, which also goes like omega to the -1. And how you do that? Well, is actually the realization that this is implemented by inserting in the S matrix some currents. For super translation, there is this so-called super translation current, which gives the following. So this, I'm just rewriting here the word identity. So if you insert this current into the S matrix, it will take the following form. There is an analogous story here. Let me just write everything and then I will explain a little bit more. I'm just trying to collect a lot of statements, and then we will see later that in the celestial holography program, these currents will be implemented in a very natural way. Let me just mention this subleading story. So remarkably, what people found is that they knew that there was this super rotation symmetry, and then they thought, okay, it seems that there is a identity between there is a relation between symmetries and soft theorem. So why don't we look for the extra term into this expansion? There's an expansion in omega, where now this subleading soft factor doesn't go like 1 over omega, but now like omega to the 0. And Cachaso and Strominger found that indeed there is a theorem, a soft theorem associated to super rotations, which now is subleading compared to the one with the Weinberg pole, but that exists. And remarkably, these statement can be implemented through an insertion of an object which looks like a stress tensor. And the realization that there was, so basically that this wild identity was equivalent to inserting a current on the celestial sphere, which has exactly the right dimension to be a stress tensor in a conformal field theory, was what I think really kicked kicked off the celestial holography program when people realized that there was something transforming like a stress tensor, and they thought, okay, maybe we can dig better into the conformal field theory structure of flat space, and we will find some constraints on the holographic nature of flat spacetimes by identifying more of these currents. So I know I was quite fast on that, so I will stop here and take any question you might have. Thanks.
Okay, let us start today's second lecture. So INFN will continue telling us about non-invertible symmetries.
Okay, well back everyone. So let's continue our journey into the realm of non-invertible symmetries, particularly in two-dimension conformal field theories. So here I summarize some of the things that we talked about in the previous lecture, and also some of the things that I'll briefly explain now. In particular, in the previous lecture, we introduced these notions, a mathematical framework known as fusion category, which is a natural generalization of group symmetries, taking into account their anomalies into some more general object, and which we used later to describe symmetries in conformal field theory that are associated with non-invertible topological defects. So as we said before, objects in this fusion category correspond to topological defect lines. And in particular, in the CFT, they are associated with this twisted defect Hilbert space. Okay. This is the Hilbert space. Okay. On the cylinder, when you quantize, this is the time, and you quantize on the circle, okay, which is punctured through by the defect line. Okay. And then there's a notion of direct sum in the fusion category, and that boils down to the fact that on the CFT side, a Hilbert space associated with the direct sum of lines splits into the direct sum of the Hilbert space associated with the individual constituent lines. And then there's a tensor product operation in the fusion category side, and that allows you to decompose a product of lines into a direct sum, and that boils down to this picturesque fusion product on the CFT side, which is a special case of OPE between line operators in 1+1 dimensions. And then there's this this notion of a dual object, which Pavel pointed out last time, and I forgot to introduce. And that on the CFT side corresponds to taking the CFT conjugate of a given line. Okay. So in any observable involving this line defects, you are free to replace this diagram with this particular orientation by L bar, but in the opposite orientation. Question? Here? For the CFT. CFT just means that it's a composite line. So meaning that if you compute a correlation function where you insert a direct sum of a line, that correlation function becomes a sum of the correlation functions in which in each summand you have the individual line inserted. Okay. And then there's the notion of the morphism, okay, in the fusion category. And on the CFT side, they simply correspond to topological junctions. These individual junction vectors are denoted by V, and they live in some juncture vector space. And that has a natural interpretation in terms of the Hilbert space over here. The generalized defect Hilbert space, a simple generalization of the above, where you have more than one lines puncturing through the circle on which you quantize the theory. Okay, so you have L1 bar here, L2 bar here, and L3 here. Okay, and this picture is related to the picture over here just by doing radial quantization on this circle. Okay, doing radial quantization, you map this point-like operator to a state on this circle punctured through by these defect lines. And the requirement of this object being topological boils down to the condition that you want to require the corresponding states in the subspace to have H and H bar equal to 0. Just like identity operator, so it can move it around, costing no energy. Question?
In this radial quantization picture, no, the choice of the morphism, how does it reflect on the cylinder? Because
right, so it boils down to a particular vector in this junction vector space. So the junction vector space is a subspace of this superspace, restricted to the eigenvalues of L0, L0 bar equal to 0. In general, that could be a dimension bigger than 1 vector space. It should in general it's a vector space. So this V, if it exists, is a vector in that space.
Okay, so you choose a basis.
That's right. So if that space is empty, that tells you that this topological junction does not exist.
Okay, thanks.
Yeah. Yes.
Are you allowing also for non-trivial junction on the trivial line? For example, if you confuse the trivial line with itself.
Yes.
And this
when you say trivial line, you mean identity line, or
yeah? Okay.
So,
are you allowing for non-trivial junction? Let's say local operators.
Very good. So here. I will get to that, but to answer your question quickly, so I think you are imagining a case when, for example, one of the 3 external legs is identity.
Also, all the 3.
If all 3 are identity, then the implicit assumption I'm making in the CFT is that there's a unique vacuum. Okay, and that will answer for you that there's a unique. There's just one-dimensional junction vector space there, and they are proportional to the identity operator in the bulk. Okay, and more generally, if you take one of these lines to be trivial, from the argument I'll give shortly, if L1 and L2 are simple, then the corresponding junction vector is again coming from identity operator taken to the line. Okay, identity operator in the bulk taken to the line.
Okay, thank you.
Any other questions? Okay, so so these are the basic defining data, and there's one more ingredient. These are this F symbol. Okay, I will not redraw that diagram again, but it essentially like a matrix that keeps track of the change of basis in the junction vector space associated with 4 external legs: L1, L2, L3, L4. Okay, there are 2 different ways to represent this junction vector space by factorizing a 4-fold junction into a pair of 3-fold junctions, and that change of basis matrix is captured by this F symbol. And the F symbol is subject to this pentagon relations, and that physically just corresponds to consistency on this change of basis operation. Okay. All right. So let's use this kind of the general dictionary to deduce some simple consequences. Okay, in particular relating to the fusion rule, that the specific features of this fusion rule. Okay, so far we have not been assuming any special property of this line. For example, this line can be decomposable, but it turns out that if this line are taken to be indecomposable or simple, there's a nice property of the fusion coefficient which can be interpreted from the point of view of its topological junctions, and this will come to that next. So let's first introduce the notion of simple topological defect line. Okay, a simple topological defect line is defined by having a one-dimensional junction vector space. Okay, between itself and its conjugate. Okay. So it's easy to see that this condition implies that this defect line is decomposable. Okay, let's see why that's the case. First of all, for any TDL, for any defect line L, okay, it's easy to see that the dimension of the junction vector space between itself and its dual has to be bigger or equal to 1. Just because the junction be something like this, okay? And you can include identity here, but you can forget about it as well because it's identity. And you can always bring the identity operator in the bulk to the line, and this gives rise to a non-trivial junction vector associated with L and L bar. Okay, so if I draw the L bar, okay, and the identity. So if L is decomposable, equal to L1 plus L2, okay, this implies that the dimension of the junction vector space must be bigger than 2. This is because this factorization, I mean, this kind of distributive property associated with the Hilbert space will defect Hilbert space will translate to a distributive property for the junction vector space. And there's at least 2 contributions coming from the fact that for each L1 and L2, there's a non-trivial topological vertex with identity. Okay. So just from this, you conclude from this definition that simple TDL must be indecomposable as we have expected. Okay. It turns out, strictly speaking, being decomposable doesn't necessarily imply simple in this definition, but this will actually lead to a generalization of the fusion category I'm talking about here. So I'm happy to talk to you afterwards about that, but let's, for the moment, focus on the case where actually indecomposable also implies this condition. Okay. Now, once we have introduced the notion of simple TDL, we can talk about the fusion product of these simple objects. So writing the similar relation over here, over there. Now, in general, there's some coefficient that appears in the decomposition of the tensor product of the two simple TDLs into all the simple TDLs that you have in your theory, okay, that generate all the non-invertible symmetries. I claim this coefficient is equivalent, it's equal to the junction vector space, dimension of the junction vector space. So to write explicitly, associated with these three lines, I, J, K, okay, defined over here. Okay, so how do we prove this? So let's focus on the simple case when Li and Lj are taken to be L and its conjugate. Okay, and L is a simple line. Okay. Okay. And we want to show that this is equal to 1 plus other non-identity simple lines. Okay, up to some degeneracy. Want to show. Okay. So how do we show this? Let's consider the torus Spanning function. So imagine the square represents the torus in the coordinates which have 2 pi periodicity, both in this direction and in this direction. Think about this as time, this as space. Okay, so the opposite sides are identified. And we insert this topological defect lines as follows. Okay, and because of the definition of the dual coming from the conjugation, I can replace this also by the original L line, but we invert its orientation. Okay, the torus has a modulus tau, as usual, to control the shape of the torus. Now, there's 2 different ways to compute this this observable, the torus Spanning function, in the presence of these 2 lines. The first way is to take directly the limit where tau goes to I infinity, okay, which means the time cycle becomes infinitely long. In that case, the torus Spanning function projects, well, essentially everything propagating in this time direction gets suppressed, and the only dominant contribution will coming from the vacuum. Okay, states of dimension 0, h equal to h bar 0 states dominate. Okay, quantizing down this circle, and this picks out precisely the contribution from the junction vector space, multiplied by this divergent factor that depends on the center charge. And Q is equal to e to the 2 pi tau as usual. Okay, it's a different way to represent the modulus of the torus. Okay, so we see this quantity shows up, which is what we want to relate to the diffusion coefficient here and here in the special case. Sorry. Sorry. Yeah, you're right. Good. Yeah, thanks for pointing that out. Yeah, tau is going to I infinity. So, yes. Very good. We can proceed in a different way. Okay, because we're on the torus and we have this parallel defect lines, we can apply the fusion of these lines. Okay, the fusion that's over here. And we use this postulated expression. In general, you have multiple terms, but suppose this term is n, okay, n times 1 with some coefficient. You have n times the contribution on the same torus Spanning function, but with no line inserted, a corresponding identity line. Okay, and then you have contributions coming from all the rest that of this right-hand side, which all involve non-trivial defect lines inserted in this time direction. Okay. Now you take the limit that tau goes to infinity again, just like before. This parting function dominates over this one. Why? Because we have the tadpole condition that tells you only identity operator can end non-trivially, can end on the dimension 0 operator. Okay, so this is computing the thermal parting function in the Hilbert space punctured by a single TDL. Okay, there's a non-trivial ground state energy that is above minus C/24. It's in this case, the ground state energy is saturated at minus C/24. So if you take the tau goes to infinity limit, this guy dominates, and you get precisely this expression. Okay, and equate these two, you conclude that n is equal to 1. Now, just to generalize, we can already use this result. Okay, so what we want to show is over here. Okay, and we can write this equation in the form similar to this by fusing both the left hand side and right hand side with orientation reversal of k of Lk. We consider the fusion of 3 objects in a similar configuration. Okay, and this will contain a piece like this. Okay, precisely this coefficient plus subleading. Plus. So this is times the identity line plus non-trivial lines. Okay, and once again, you can go through the same argument. So go to the torus. And now you have 3 topological defect lines inserted along the time cycle. And in the limit where tau goes to infinity, playing the same game, you find the dimension of the junction vector space goes up, multiplying the divergences, the exponential divergence is due to the Casimir energy. Okay, and doing the same comparison, this tells you that indeed this fusion coefficient is the dimension, the complex dimension of the junction vector space. So from time to time, just to save some writing, I will drop the L when I label the defect lines, just to save some time. Okay. So this is a very simple formula. Okay, but the implication is actually quite deep. Okay, depending on how you think about it. But there's a perspective that was kind of emphasized in the recent paper from Choi, Cordova, Singh, Lan, and Shao. I think it just appeared some weeks ago. Okay, they give a very nice interpretation for this formula and this generalization to higher dimension, which I want to say a few things about here. Okay, so you can think about this as the Panin function or precisely the Panin function on S1, okay, of a topological quantum mechanics. Okay. In other words, it's just a one-dimensional TQFT. So one-dimensional TQFT is nothing but a bunch of ground states with energy 0. Okay. And the fusion coefficient is the Panin function of this topological quantum mechanics over the manifold, which is precisely the manifold on which you wrap the line when deriving the fusion. Okay. This generalizes. So this is in d equal to 2. For d higher than 2. Okay. If you again consider this kind of non-invertible symmetries, say of codimension 1, this fusion coefficient will be replaced by a Panin function of d minus 1 dimensional UQFT. Okay, and as you can imagine, UQFTs in higher dimensions are much more interesting than in one dimension, and that will lead to interesting structures for or different properties for this kind of fusion product. In particular, the Penning function. This Penning function is no longer required to be integral, okay, on general three-dimensional manifold. Okay, so that will lead to kind of various exotic but now understood properties of the fusion rule in higher dimension. Yes.
Is this like a proven statement, or is based on yeah?
This is I think as far as it's not a proven statement. It's a statement. It's a kind of a conjecture, and it holds for all the examples we know at the moment. Okay. And it will be good to understand to what kind of generality this is the statement. Yeah.
Because in higher dimensions, I wouldn't even know to define a simple object very well. So you know, a lot of things.
That's right. Yes. So this nice junction vector space I'm talking about in higher dimension, the junctions. I mean, if you talk about generic junction, it will be point-like. You can do, but if it's a non-generic configuration of this defects, the junction is typically also not zero dimension. So the junction vector space will involve some topological lines and so on. So it's more complicated. Yeah.
It's a very nice idea.
Yes, it's a very nice idea. And I think I agree with you that it should be kind of more developed, should be developed further. Right.
Sorry, can I ask,
Sure.
Is there some intuition why this TQFT lives in one dimension? I mean, I naively would expect that the TQFT lives on the junction, so zero dimensional.
The TQFT lives on the, so because on this fusion picture, the two manifolds are wrapping the two defect lines are wrapping homologous manifolds. Okay, and you can take it to be, I mean, essentially identified as far as topology is concerned. And the TQFT lives on that one-dimensional manifold. Okay. It is true that when you look at the junction, then the TQFT, only operators in the TQFT shows up in the junction because there's no way for it to propagate anymore.
Yeah, because this is related to a question I did yesterday. That in higher dimension, I would expect that if you look at the picture with the junction, yes, the three defects can in principle live on different manifolds.
That's right. So for example,
where does the TQFT live?
Yes, you mean it can come out, for example?
Yes.
Right.
And so where does the TQFT live? On which of the three manifolds?
Yeah, so the TQFT here, so this is a very restricted statement. It's a statement about doing this particular fusion on parallel manifolds that are homologous. Okay, and the TQFT lives on that manifold.
Okay, thank you.
Yeah. So I agree with you that there should be generalization of this statement. We have more complicated configuration of these topological defect lines, but it's still to be developed. Okay, that's a very interesting question, but it's beyond what I'm talking about here. Let me just point out the similarity to this. I think some of you are familiar about similar kind of fusion product that appears in supersymmetric gauge theories. For example, study Wilson lines in 14√2 theories, and you encounter similar fusion rule for the BPS lines. Okay, in that case, there also a similar interpretation of these coefficients. Okay, in that case, you're talking about the fusion product of supersymmetric lines. As I mentioned, generically, if you're just taking the fusion product of line operators, the fusion product singular is not well defined. But for supersymmetric lines, there's a way to regularize the divergence in supersymmetrically, and that gives a well-defined fusion product. And in that case, the coefficient also has a very nice interpretation. It has the interpretation as the supersymmetric index of quantum mechanics. Okay, it's not a topological quantum mechanics anymore, but the Penning function is replaced by the supersymmetric index. Okay, so this is just a comment for people who study these line operators. Okay, this Nijk correspond to SUSY index of certain quantum mechanics. Okay. So a useful reference is the paper from Galto, Moore, and Nesky. All right. So the next thing I want to talk about is it's a symmetry action. Okay. Of this topological defect lines on potentially twisted, or in other words, defect Hilbert space. Okay. Because this is the one place that really distinguish the non-invertible symmetries from invertible symmetries. Okay. So what is the kind of action we're looking for? So as I already said before, the defect Hilbert space comes from quantizing on the cylinder. Okay, where quantizing on the spatial cycle of the cylinder, that's punctured through by a defect line. Let me call it L1. Okay, and say there's some state inside this Hilbert space, which I've been calling the defect Hilbert space, labeled by L1. I want to define, without the defect line, or as I already said before, the action of the topological defects on the Hilbert space on S1. They correspond to encircling the corresponding operator on the plane, right? So as before, we have this picture. This enclosing picture, after you shrink the defect line, because it's topological, you can shrink it, and the local operator you produce after shrinking encodes how this defect act on local operators. These operators are in one-to-one correspondence with the states. So this is equivalent to some operation on the state. In the Hilbert space with no twist. Okay. Now we want to generalize this notion to the case in the presence of a twist, okay, in the spatial direction by this non-invertible symmetry. So the kind of intuitive picture you want to draw is something like you want to include another topological line, okay, say L2, along the spatial direction, okay, wrapping this cycle. Okay, but for this to define a symmetry, as we know, symmetry is equivalent to topological property of this various configurations in these lectures. You want to make sure that this junction formed by these lines to be topological. Okay, but we already know what these junctions are. Okay. So first of all, let me write down the representation of the same operation on the plane using the usual mapping between the cylinder and the plane. And that'll correspond to this kind of diagrams. So this is the operator corresponding to this operator in the defect Hilbert space. And I'm drawing the same diagram, but just mapped to the plane. Okay. So to specify the symmetry action, we need to specify the choice of junction. As we said before, a convenient way to specify a junction involving multiple external legs, more than 3, is to resolve this junction into threefold junctions, okay, for which we treat as basic building blocks for higher fold junctions. So there are 2 different ways to resolve as kind of as the same case as for how the F moves arise, okay, and give rise to this 2 different configurations. Okay, and in general, here could be some intermediate topological line that appears in the fusion product of L1, L2. And similarly, another diagram you can draw, which corresponds to a different way to resolve this 4-fold junction. Essentially, you're resolving in 2 different ways, like this way and this way. Okay. And in general, this could be some other topological defect line if the fusion product is not commutative. where L4 is inside is a a potential simple line appear in the fusion product of L1, L2. Okay, if L1, L2 have a commutative fusion product, this can be taken to be the same set, but in general they could be different. And we call these diagrams lasso diagrams. Okay, just because how they look like. And these diagrams define different actions of topological defect lines on the twisted Hilbert space, in this case twisted by L1. Okay, there are different actions. They correspond to, in this picture, different choice of the junction vector. Okay, and even more generally, you can even have a diagram where the internal line that is immediately attached to the local operator that defines the twisted sector can be different from the outgoing line to the end. Okay, by considering more general junctions over here. So for example, staying to the case when this internal line is still labeled by L1. Okay, this outgoing line could be, say, some other line L4, not different from this L4. Okay, and what this diagram means is that after you shrink, okay, I do not need to draw the other arrow. I mean, the lines goes to infinity. After you shrink the topological defect network, okay, that's encircling this operator with these various junctions, what this gives you is an operator attached just to the L4 line. Okay, some other operator. Let me call it coming from all this transformation. Let me call it phi prime. Okay, the location doesn't change, but it becomes starting from operator that's twisted, that's attached to the topological defect line labeled by L. You end up with operator attached to the topological defect line L4. And what this means is that this defines operation, a linear map from the defect Hilbert space twisted by L1, okay, which correspond to these operators, to the defect Hilbert space twisted by L4. Okay. And the point of non-invertibility is that these maps, each individual maps, are in general not invertible. Let me call this map F. Okay. And I should also say that in the invertible case, you will not have these non-trivial maps if L4 is different from L1. Okay. So in the non-invertible case, the first non-trivial thing is that when you restrict the case when L1 and L4 are the same, this map is in general not invertible. Okay. And furthermore, there exists non-trivial maps between the Hilbert space twisted by L1 and L4, even when they are not the same. Okay. So that's the two features that distinguish the action of symmetries on the twisted Hilbert space in the case of non-invertible symmetries versus that of the group-like symmetries. Yes.
Do you get any like consistency conditions on these maps because of the pentagon? No.
Yes. So yes, these maps are not independent. Okay. These maps are closely related. For example, these two are related in a way by the F move. Okay. So what I'm trying to say here is that you can, if you just want to have a most general action, okay, of this kind of a TDL encircling an operator attached to another TDL, the most general action is specified by the choice of junction vector over here. You can represent this junction vector purely in these spaces by including all the L3s over here and all the choice of the threefold junctions over here. You can also do the same thing over here. Okay, and these two different bases are related by the F move. Okay.
I was meaning, okay, maybe if you take like two operators inside, no, because you can just draw the diagram of the pentagon then. Here you do the diagram of the F symbol, no?
Sorry, maybe I'm not completely sure what you're talking about here. the F move just concerns.
No, I know.
Yeah.
I understand.
Yeah.
No, I will maybe in the discussion.
Okay,
sorry.
Sure. Yeah. Okay. And I don't have time to go into that detail, but the action of symmetry on the twisted sector is in general a very important object. Okay. For example, in the case of group-like symmetries, the anomaly associated with that symmetry is equally encoded. So it is encoded by the non-trivial phase that appears in F move. Okay, but it also equally encoded in the symmetry action in these twisted Hilbert spaces. Okay, in that case, L1 and L4 are the same. Okay, and in particular, you observe this phenomena that the symmetry, the group-like symmetry, acting in the twisted sector can develop projective representations. Okay, even though acting on the untwisted Hilbert space is faithful. Okay, the linear representation. Okay, and there's some generalized notion for this non-invertible symmetry, but I will not get into that general detail now. Okay? Instead, let's move to another physical object. Yes.
Just to make sure I'm understanding,
Yes.
if the symmetry was invertible,
yes,
this junction could still be non-trivial. I mean, L1 could be different from L4, and this means that this symmetry is giving an automorphism of the set of lines in the case of invertible. I mean, you're picking L2, and it's acting on the.
So if all the lines are invertible,
yes.
Okay, then for this junction to be topological, then L4 has to be same as L1. Just from the junction, as we said before, the topological junctions are only if this condition are satisfied. Okay.
Okay.
So if this is if these are all invertible, L3 has to be the product of L1 and L2, and because this is already L2, this has to be L1.
I see.
Okay. Of course, you can choose to insert something that's not topological over here. Okay. But then you cannot do the procedure to shrink the diagram down to a local operator, like what I'm doing here. So you have some two-point function, and there's a non-trivial OPE, which you can still study, but it will not give rise to this nice linear map between local operator and local operator. In that case, the OPE coefficient, in particular, of this non-trivial local operators would enter into this map. Okay. Okay. The next important physical quantity that encode information about fusion category in the CFT is the notion of the VEV of a topological defect line. Okay, which is also known as the quantum dimension of L in the fusion category. Okay, this is a very simple notion. Okay, so the VEV is defined as the expectation value of the topological defect line on the cylinder. Okay, so you have a cylinder. Okay, and you have this topological defect line inserted in this orientation. Okay, so that's the definition. There are a nice property of this topological defect line. Okay, on infinite long cylinder, you can consider infinite long cylinder, and on which you insert, a composite Li and Lj. So call this Li, and insert another Lj. Okay. The fact that you have this fusion rule. So for now, I'm always taking the lines to be simple unless I say otherwise. Okay, because on the infinite long cylinder, everything is projected down to the vacuum. The state that propagated in this direction is projected down to the vacuum. It means that the VEV will satisfy the same polynomial equation. Okay. So you can think about this as some kind of cluster decomposition on the cylinder for these lines. Okay. Sorry. That's right. That's right. Yes. Yes. But here I'm just using the fact that down the cylinder, it projects to the vacuum. Okay. So that all in the intermediate, and because they're topological, can make them as arbitrarily far apart lines. Okay. All right. So this means that the vectors are highly constrained by this polynomial equation, this very particular property that the coefficients are positive integers. So these are going to be very special algebraic numbers associated with these vectors. Now there are additional constraints on these vectors coming from unitarity. Unitarity would imply, in particular, that these vectors are actually bounded below by 1. Okay, this is a slightly, oops, I did it again, sorry. Slightly non-trivial to see, so let me go through that argument. Okay, the argument actually is a very simple argument involving the consideration of torus, which will come back. So let's it's worthwhile to go through it in a little detail. Okay, but let me first say explicitly. Let me first say the consequence of this. Okay, so in the case when Li, these lines have expectation equal to 1, that's the case when it's invertible. Okay, because this condition, going back to this equation, implies immediately that only one fusion coefficient can be non-vanishing and it has to be 1. Okay, so there can be at most one term on the right-hand side of the fusion product, and so they are invertible. Okay, they generate some group-like symmetry as usual. And if the VEV is bigger than 1, it's non-invertible. So in other words, if you have some line defects, which is topological, a quick way to diagnose whether you have a non-invertible symmetry or not is just to compute this cylinder expectation value. And if you find it to be bigger than 1, then you know right away that you have a non-invertible defect. Okay, emphasize this is the case in 1+1 dimension. This statement does not hold in higher dimensions, precisely because the coefficient will depend on this non-trivial TPFT. Okay, which is the dependent function no longer an integer in general. Yes. Question?
Yes. Sorry. But yes. If you normalize differently the lines,
yes, you
get different quantum dimensions.
Good. So okay, we'll come to that. Well, the next dimension will make that clear. Okay, if it does not, ask me again. All right. So how do we derive this statement? Okay, and this derivation should also address this question. So we'll be using locality. Okay, in particular, locality of the quantum field theory, in particular in this case of 2D CFT, define a torus with the insertion of a line. Okay, so the object we'll be studying is this the torus spanning function. Okay, with the defect line inserted. Let me call this L. Okay. The locality of the Euclidean CFT or quantum field theory in general implies that we are free to compute this spanning function. So let me label this spanning function. So we're free to compute this spanning function in different ways. We're free to quantize the theory in different ways. So we can quantize on this spatial slice. And this defines, naturally, this spanning function. Okay, with upper L, just to denote this particular choice of quantization, which can be interpreted as a trace over the Hilbert space on this spatial cycle, which is not punctured by any defect line. So it's ordinary Hilbert space, weighted by the action of the line, denoted by L hat. Okay, the same L hat that appeared over there, and weighted by the usual Hamiltonian evolution factor. Okay, in 2D CFT are determined by the L0 and L0 bar. Now, there's a different way to compute the same spanning function. Okay, so instead of treating this as direction of time, we can treat this direction of time. That's a consequence of locality. Okay, that you can quantize the theory in different way. And in this case, so that's equivalent to S transform. Okay, so if I still think about this direction as time, I want to rotate my picture. And as a consequence of that rotation, the line now, so I'm going to do this direction actually, which is the convention for the S transformation, 90-degree rotation this way. Okay, and this defines naturally the Poynting function. Now, for the it's a Poynting function, it's a thermal Poynting function that's represented. So let me write in terms of the inverse, or the S transformed values of the shape modulus of the torus. So this is T2 tau. Okay, and this is interpreted now as the trace over the Hilbert space, the defect Hilbert space, because now the defect punctures through the circle on which you quantize the theory. But because there's no other defect insertion, this leads to this simple thermal Poynting function with no additional insertion. Okay, and Q tilde is the analog of Q when so Q is as before, Q is e to the 2 pi I tau, and Q tilde is just e to the minus 2 pi I over tau. Okay. Now, the fact of locality equates these two sides.
Are you assuming C equals C bar?
Very good. Okay, so let me forget about subtlety with the gravitational anomaly under the modular transformation, and for simplicity, focus on the case when C is equal to C bar. Okay. And in that case, the right-hand side has a property because it's a trace over Hilbert space. Okay, Hilbert space is some vector space, in particular some vector space. It has this decomposition. Okay. Into characters. Okay, and because we have a topological defect line that preserves the Rosaro symmetry, this will decompose into characters as I'm trying to see of the following form. Okay. Okay. But for now, actually, we will not need this specific form. All we need is the fact that this is positive if we restrict to the case when tau is equal to IT and tau bar is equal to minus IT. Okay, because these coefficients are positive integers. Okay, and each of the terms are positive. Okay, so I mean, okay, you don't really need this. You just stare at this with this assumption is already positive. Okay, because each weight is positive, and you're summing over some degenerate, summing over all the states. And what this implies, and okay, the reason I write this is to address the question. Okay, this is not required for the derivation over here, but I write this to address the question, is because if you rescale your what do you mean by L here, it will be in tension with this being a a quantized integer. Okay, so you can take a direct sum of this line. That is fine because it's going to retain its integrality, but you cannot apply by arbitrary number. Okay, and that's what in what sense locality is crucial. In specifying these lines. Without that, you can multiply by arbitrary phase, for example. There are still some subtle kind of counterterm you can introduce for the line, but that's not relevant on the cylinder with a flat geometry. Okay, so there are subtleties of additional phase factors that you can introduce for the line by introducing one-dimensional counterterm. If you're interested, you can ask me afterwards, but it will not show up in this context. Okay. All right. So what does this equality imply? This equality implies, so if we specify to this case and take the limit that t goes to infinity, okay, on both sides, Once again, on the left-hand side, because t is tending to infinity, q is going to 0, the term that dominates the left-hand side will be the contribution from the L hat acting on the vacuum. So here I should write L hat. Okay. So this means that the VEV of this line, which is the expectation value of L hat on the cylinder, okay, is equal to the limit of something that's manifestly positive. Okay. Sorry. Sorry. Which exponential before? Here? No, I've moved. I'll start from here. Move it to the right hand side. Good. Okay. Okay. So we're halfway there. Okay. We proved it is bigger or equal to 0. We have not shown that it's bigger or equal to 1. Okay. For that, we use the first effect. Okay. That if we take the fusion product of the defect line L and its conjugate, taking them to be simple, we have on the right hand side 1 plus other non-trivial lines. Okay, and from this property, we already know this is bigger or equal to 1. Okay, and then we use the CPT invariance of a general quantum field theory that says that these VEVs are the same. And as a consequence, we have shown that the VEV of L is bigger or equal to 1. Okay, so I went through this kind of argument in detail because this is how this is actually how various non-perturbative constraints from this fusion category symmetry have been derived in 2 dimensions and also in higher dimension. It's a generalization of this game using the locality of the path integral, whichever direction you call time can lead to different expressions, and that can lead to constraints on what kind of phases can appear under a symmetric RG flow. Okay. So now I just want to introduce the general data. After this basic building block, let me just introduce the general data for a CFT enriched by non-invertible symmetries. Okay, so whenever you have a symmetry, apart from trying to study constraint from the symmetry on the original CFT observables, okay, and another thing one can study is the additional observables that are brought to life because of this additional symmetry. In particular, those leaving the twisted Hilbert space from inserting this vertical duality, vertical non-invertible defects. Okay. So CFT, we call that CFT without defects. Okay, in 2 dimensions. The basic data is captured by the Hilbert space on S1, okay, which is related to the local operators by the radial quantization. And together with the OP coefficients between these local operators. Okay. And this data are subject to bootstrap constraints. Which are again consequences of the locality of the Euclidean observables. For example, the 4-point crossing equation can be thought of as consistency in cutting and gluing the 4-point observable on a sphere with 2 punctures. You can cut along this cycle. And you can also cut along the other cycle. Okay, they give you 2 different OPE channels, and the equivalence between decomposition in the 2 OPE channels coming from inserting complete set of states on the circles leads to the bootstrap constraint that constrain this data. Okay, And there's a similar relation for the torus one-point function. Okay, and it's a non-trivial fact that a set of data that satisfy the two kinds of consistent conditions. There are infinite set of consistent conditions because you need to consider arbitrary insertions labeled by states in here. Okay, and similarly here for the one-point function. But the non-trivial fact is that once this set of conditions are satisfied, this defines the consistent CFT. Okay, so all the cutting and gluing consistent conditions on arbitrary general Riemann surfaces are automatically satisfied once these two basic moves fulfills. This generalizes with DBLs in a natural way. So the moment you have topological defects in the CFT, as I said, there's this additional structures that appear. Okay, just from the locality of the conformal field theory, you have this defect Hilbert space. Okay, and you also have this additional OPE coefficient. Sorry, so let me write it here. You also have this additional OPE coefficient that involve operators now in the defect Hilbert space. So they can generally be represented on the plane by some diagram like this. Okay, where the external legs are some topological lines. And there's some topological junction leaving here. But the external operators correspond to operators in the corresponding twisted Hilbert space. So these are the additional data you bring to the game. And to fully specify non-invertible symmetry in the CFT, after having some evidence for such objects, is to solve for these quantities. Okay, and they are subjected to similar bootstrap equations. For example, the 4-point function, once again, but now attached to a network of this topological defect lines. Okay, so all these lines are not just mnemonic for OPE exchange, but are extra defect lines. And depends on whether you cut in this direction. Okay, I don't want to draw the circle again, just to mess up the diagram. Or this direction, okay, inserting complete set of states, and last leads to constraint on this data. So this provides, there's a similar generalization for a torus one-point function, which I'll not draw. This provides an axiomatic approach to identify non-invertible symmetries into DCFT. Okay, so having non-invertible symmetry into DCFT, because we discussed, if we assume the existence of this topological defects, it will imply all these structures that satisfy cutting and gluing as a consequence of locality. So if you are given just abstractly CFT data like the local Hilbert space and this OPE coefficient, the thing you need to do abstractly to identify a non-invertible symmetry in the CFT is to solve for this additional data. Okay, if you find a solution, then you are sure that you have this non-invertible symmetry. Okay, but as you can see, this is going to be a formidable task for general CFT. Okay, because there are many bootstrap. Yeah, so I should wrap up. Okay. Right. Okay. But as we'll see, there are additional physical arguments that allow you to infer the existence of topological defects without solving this equation explicitly. But these equations can be solved explicitly in rational conformal field theories. Okay. Let me not get into the detail, But let me just say that in the next lecture, we'll discuss explicit examples that realize the symmetries and produce solutions to these equations without actually solving these equations explicitly. Okay, I think I'm going slower than expected, but that's fine. So let me stop here and take questions.